Hey everybody, it's Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival. And today I'd like to talk to you a little bit about what's known as the Haber process for nitrogen fixation, and about Le Chatelier's principle, which is a concept which allowed Haber to design a reactor that would carry this reaction out. Now, to set the stage just a little bit, this reaction was developed into an industrial process in the early 1900s around World War I by Fritz Haber. And what Haber was after was ammonia so that he could fuel a war machine, so that he could feed and create explosives and ordnance for a very large German army. And in order to do this, in sort of an ironic twist, he used the idea of a French chemist, Henri-Louis Le Chatelier, who discovered, or more accurately, observed, that we could shift equilibria if we placed them under a stress, and those equilibria then try to relieve the stress. So what we're going to do today is take a look at how and why this reaction is so difficult to run, and then how Le Chatelier's principle allows us to get around that issue. Let's get started. The Haber process involves the reaction of 1 mole of N2 gas with 3 moles of H2 gas to form 2 moles of ammonia. And it's an equilibrium, and it's also a really tough reaction to get started. So Haber had to heat this reaction to 400 degrees centigrade and compress it to 200 atmospheres of pressure in the presence of an iron catalyst, all just to get that nitrogen-nitrogen triple bond to break and activate the reaction which formed the ammonia he wanted. So this reaction is a very disfavored equilibrium, even under these conditions. And what Haber most likely would do is sit down with his pen and paper, just like any good Gen Chem student would, and try to determine the amount that he would get at equilibrium from such a reaction. So let's do that. I'm going to use my reaction to create a rice table. Now I've got my N2, my H2, and my ammonia, or NH3. Now at 200 atmospheres pressure, my starting materials would be 50 atmospheres of N2 and 150 atmospheres of H2 because of the reaction stoichiometry. I can then determine the change from the coefficients in the reaction and get functions for the equilibrium concentrations of all 3 gases simply by adding the change to the initial conditions. Now, because I know that this is going to be a very disfavored equilibrium, because the equilibrium constant is 10 to the negative 5, I can assume that the change x is negligible compared to the starting concentrations or pressures of N2 and H2. So I'm going to omit those from my calculation to make the math a little bit easier. So now I take my equilibrium concentrations and I put those into my equilibrium constant expression. Solving for x gives me about 3, meaning that at equilibrium there will be about 6 atmospheres of ammonia, even though there's about 50 to 150 atmospheres of N2 and H2 respectively. So this is a pretty mild amount of conversion here. This is only about 10%, and it's far less than we hope to get in any particular process, and certainly far less than Haber was hoping for. What this means is that we have to use a tremendous amount of nitrogen and hydrogen to make just a little bit of ammonia gas using the equilibrium that Haber had developed. This is obviously a problem. So let's think about this equilibrium in another way. Let's look at it graphically. So I've set up a reaction here where I have 2 areas of my box, and I'll be putting the reactants in one side and products in the other. Now, of course, the reaction is all taking place in one container, but I'm going to separate them out so they're easier to see. So let's start with a large amount of H2 and N2 gases. As the reaction starts to take place, I form a little bit of ammonia, but that ammonia is constantly being reconsumed in the reverse process. So even though the system is constantly producing ammonia, there's never a very large accumulation of it. And this was the problem that Haber was facing. That kind of yield would not have made him happy. But there's a solution, and it's offered by Le Chatelier's principle. So let's take a look at our reaction one more time, but this time we're going to use Le Chatelier's principle and a little bit of engineering to solve the issue. What we're going to do is, as our NH3 product forms in the gas phase, condense it into the liquid phase and drain it out of the reactor. So we'll be collecting the ammonia as it forms. So let's get our starting materials ready and let the reaction go. So it begins by forming a small amount of ammonia. Now I'm going to freeze it in time here, because this ammonia, instead of going back to the starting materials, it's going to be condensed and collected and therefore completely removed from the system, which will then try to reestablish the same equilibrium. So as you can see, every time ammonia forms, I siphon it off by condensing it. And the system is constantly trying to reach equilibrium, but it just can't get there because I'm not allowing it to happen. If we do this properly, by the end of the reaction, we can get a nearly quantitative conversion of nitrogen and hydrogen into ammonia gas. And clearly, this would mean for Haber reaching his goal. And unfortunately for Le Chatelier, World War I continuing onward. A little bit of a backfire there. But regardless of what you think of the politics of either one of these two men, what's undeniable is this. The innovation of Haber and the observations of Le Chatelier combined into a process which we currently use to feed the world's population in the form of nitrogen-containing fertilizers produced in Haber reactors that are still being used to this very day. It's powerful chemistry, folks, and a great example of Le Chatelier's principle. That's all for now. Professor Davis from ChemSurvival.com and the YouTube channel ChemSurvival. I'll see you on the next video.